Hey, I'm back. Sorry for that delay. I had a bit of a little thing I had to do here. Anyway, welcome back. Week number 11. So we're coming down to the wire. Okay. Don't forget next week, quick couple of announcements. Next week is exam number 4, covering chapters 10 through 12. We'll be done with chapter 12 today. And 13 also, we'll be done with that also today. That's very short. We're getting into the realm of reasonably short slides. So a few weeks left. We're going to end up with some what I call study days, meaning that I'll be here for lecture, for discussion. You bring in any questions you want and we can go over them. It's going to be roughly approximately maybe one chapter. I'm going to do chapter 12, knock it out today, do chapter 13, and then we'll leave it at there. Next Friday will be chapter 14. I believe the Friday after that is Thanksgiving. Then we come back and we'll knock out 15 and then 16 the following week. So it's basically going to be just one chapter. So we probably won't be utilizing the full time here. So good opportunity to come in and start preparing for the final. The final is comprehensive and of course online. So start getting ready for that. Catch up on your assignments. Let's see what else. Nomenclature exam. Quite a number of you have done it and reached that 80% threshold. Again, the question that is asked is it required? Well, it's any assignment, okay? So like any assignment, you know, you do it, you don't do it. I put a 0 in there to demonstrate that what effect that has, if you've not done it, I should say, what effect that has on your grade. So if you're on the border, it could kick you into a better grade or it can drop you into a worse grade. So, but if you're in the middle there in the grade scale, you know, doing it, not doing it may not push you one way or the other. Okay. So FYI. Now I do go in there once you complete your trials, you have unlimited trials. I go in there and I check because Canvas is still learning of what is accepted as a good answer, and we're teaching it as we go along. So I go in there and I check, and I do give credit for answers that are correct, but for whatever reason, Canvas doesn't recognize it as correct. Okay. And keep in mind, the SCC department on policy says you got to score at least an 80% to consider it passing. So anything less than 80%, the score gets converted back to a 0. Okay. And you have unlimited attempts. I repeat that, unlimited attempts, so you can do it. If you're at the 80 and you want to improve it, by all means, it won't. You can still continue to do that. A quick note: some of you have done the homework, for example, and maybe just did the first attempt, and you were happy with the grade, and that's fine. Yeah, it's your choice. But you might have a second thought and say, well, let me go back and do the second attempt to improve my grade. Okay, that's fine. You got 2 attempts. However, Canvas, if you go back to an old homework exam, homework assignment, which was due, last month, and you do the second attempt, it treats it as late. Well, of course, it's not late because you did it within the time limit of the first time. So if that happens, you go back and do your second attempt, and it's better. It's a better score that you want to keep. Let me know, and I'll make sure I take off the penalty for that, because Canvas, like I said, doesn't recognize that you completed it within time limit. I'm doing my second attempt, and then it's okay to do a second attempt without putting a penalty on it. Okay, Canvas doesn't understand that. Okay. Any questions, comments, concerns? All right. Don't forget, Drs. Kim and Dr. Dana from GCC have been offering weekly work study sessions. I gave the link to everybody. feel free to jump in there. They're aware that SCC students will be coming in. There's no problem with that. And so use that as an additional resource along with the tutoring that's offered by ACC for chemistry. Okay, so we're getting down to the wire. You need help, I'm an email away. You're welcome to jump into my Tuesday, Thursday classes at any time, no problem, because all three sections are roughly the same. In fact, you are just half a chapter behind chapter 12. And it's only because we meet once a week. But after we're done, you have been caught up with my Tuesday, Thursday section. So feel free to jump into those to get an additional information with respect to whatever chapter it is. So you get Tuesday, Thursday, and come back on Friday, and you're familiar with it, okay? With the topics that I'll be talking about. All right, any questions? All right, if not, I will proceed where we left off.
I have a quick question about the
Sure.
the nomenclature test.
Yeah.
Whenever you type in the names, like do you capitalize the first one and not capitalize the second one, or do you like capitalize the first one and the second one?
Canvas answer that by capitalize the first one and not the second one. Okay. Me, hey, as long as you got the name, I'm happy. So if you got it right and you did not capitalize it and Canvas did not and content wrong, shoot me an email. I definitely will fix that. Okay.
Okay, because I didn't know how to tell if they did or not, but
yeah,
because I got the 80 out of 100, but like obviously I want a better score.
Of course. So yeah, normally first name is capitalized, and then the second one is not. It's just like a sentence in English. Your first word is capitalized, and the subsequent words are not, unless it's a pronoun or something like that. But either way, I don't have a problem whether you capitalize it or not. Even a simple thing like the Roman numerals, Canvas does not understand the space. It treats it as wrong. So you say, let's say you type in iron, I-R-O-N, and then you put a space, and then you put parentheses, Roman number 3, and ends parentheses, and just says chloride. Canvas will not recognize that extra space after the end, so counts it wrong. But
okay, I think that's what was, but why it took off points for
right.
the Roman numerals.
So let me know. I go in there periodically and I check. I will through after everyone's done, and I check it. So I just went through a batch this morning, and I think it pushed a grade from 70 up to into the 90s because of Canvas not recognizing that whatever, I don't want to say what student, but whatever they typed was correct, and it's acceptable. And like I said, Canvas is not AI, and it doesn't recognize that. We have to teach it what is acceptable and what is not acceptable with respect to an answer. And things like capitalization and spaces, it doesn't know. Okay. All right. Hopefully that answered your question. All right. So we actually ended up on slide 12, but I want to back it up a little bit, because what we've been talking about is the concept of the mole. Now, this whole concept of the mole is very important, because we need that to be able to calculate quantities with respect to chemical reactions. Now, we can't go directly from, say, grams of A to grams of B, because there isn't a common factor that they've had, with the exception of the concept of the moles. With the concept of the moles, I can go from grams of bananas to grams of apples, but I got to go through the moles. Okay, that's what they share. And so we learned about the moles, which is nothing more than a number. Okay, Avogadro's number is 6.02 times 10 to the 23rd. Items, quantities, whatever you're counting. Just like the dozen is nothing more than a description for a number of 12. Okay, it just so happens that the chemist dozen, as we call it, is much, much, much bigger than 12. And so we went through the exercise of converting grams to moles, okay? And going from moles to grams. For example, the question we did earlier last time was how many grams is 1.667 moles of oxygen gas? And so we need to talk about, we need to calculate the molar mass. And so we're at the point where we started off with learning about the atoms and learning about the elements, I should say, and then specifically kind of focus on the A in the Roman numeral 1A to 8A. Focus on those, and we talked about which ones are going to lose electrons and gain electrons to form ions. And we learned that the metals will form cations and the non-metals will form anions, and that we put them together with enough of each to cancel out the positive and the negative. And so we put them together to write a formula. We talked about the elements, the diatomic elements that always you recognize, and we have to put on O2, for example, like oxygen. Okay, we talked about which elements are liquids, which ones are solids, which ones are gases, because we need to write that information when we write a chemical formula and we give it the physical state, okay? And so we've been putting everything together now. We're gonna start putting, we took the elements, made the compounds, we start the compounds reacting with each other. Then we learned to balance them. We learned about the different types of reactions, only 6 types of reactions. Then we learned about balancing these reactions, because those coefficients in front of the compound gives us a ratio between reactants or a ratio between reactants and products. And that ratio is what we're going to utilize to be able to convert from compound A to compound B, that mole ratio. So it all comes back to the mole. So we've been learning how to work the mole, so to speak, okay? And so you can see here, look at the trend. We've said 1.667 moles of oxygen. And what do? To get it back to grams, we multiplied it by the molar mass, okay? And the molar mass is nothing more than adding up all of the atoms within the structure of the compound and applying the atomic weights for each individual atom and tally up that number, and we ended up with molar mass, okay? Oxygen is diatomic. Notice the key word oxygen gas. They didn't say oxygen atom, because if they said oxygen atom, and we're dealing with just one, right? And we can put there for the atomic weight 16. But we know that oxygen gas is diatomic, therefore the molar mass is 32 grams per mole, okay? All the molar mass, the atomic weights, and the molar mass have the units of grams per mole. It's a ratio. And once we got a ratio, we can write it with, in this case, grams in the numerator, or invert it and say moles in the numerator. So we can write as grams per mole or moles per gram. Which one we need depends on the question. And so we're going to emphasize again the units to help us set up the problems. Okay, just like we did in that chapter 2 or so, that we did conversion of metric to English. We had conversion factors that we can set up as a ratio. And then setting it up properly, things canceled out. For example, you can see that moles of oxygen, the moles cancel and the moles cancel, leaving us with units of grams, because that is what we're looking for, units of grams. You do the math and it ends up that 1.66 moles of oxygen corresponds to 53.34 grams of oxygen. And the second example here, we're going from moles to grams, okay? And so we got 45 grams of silver, so we need the atomic weight, okay? When we talk about atomic weight versus molar mass, the only difference is this. When I say atomic weight, we're talking about the single element. When I say molar mass, I'm talking about the atomic weights of all the elements within the structure, within the compound. So the atomic weight of silver, which you get from the periodic table, is at 107.87 grams per mole, okay, grams per mole. but we're looking for moles. And so therefore our conversion factor is set up to the atomic weight is set up with moles in the numerator, grams in the denominator, because we want our grams to cancel out, leaving us with units of moles, and do the math. As 0.42 moles correspond to 45 grams of silver. Okay. Then we did, how many grams is 0.554 moles of water? Notice the moles earlier, we've been talking about 1 mole, 2 moles, and so forth. Now the moles are getting a little bit smaller. That's okay, because we generally don't work with big numbers. We're working with small numbers. So 0.0554 grams of water. Obviously, we need the molar mass of water. We had done that example before, but 1 oxygen, 2 hydrogens, that corresponds to 18.02 grams per mole. Okay, that is the molar mass of water. And we set it up with grams in the numerator because that is what the question asks for. And their moles cancel out properly. So now you just do the math, and we end up with 0.998 grams of water. And so almost 1 gram of water, corresponds to 0.055 moles, very small amount, okay? But even that small amount, if we convert that to actual molecules by multiplying this by Avogadro's number, that's a pretty big, hefty number, okay? And then we did one more example. Now here's an example that we put multiple conversion factors, okay? And we are in grams, and we want to know how many atoms we have of potassium. And so that the fact that they're asking for the number of atoms should direct you to, I'm going to use Avogadro's number here. Okay, and so this could be atoms per mole. I call it atoms because that's what we're looking for. It could have been bananas. I could have put bananas per mole. Okay, but they're looking for atoms. And so those are the units for Avogadro's number. So we set it up with what we given, which was 4.75 times 10 to the 16 atoms. We use the conversion factor of Avogadro's number. We're dividing, okay, by Avogadro's number. And then we multiply it by the atomic weight of potassium, which is 39.10 grams per mole. Checking your units, you see that all those units cancel out, leaving us with grams of potassium. And so again, give you some perspective as to how small these atoms are, because this number here, 4.75 times 10 to the 16, that's a hefty number. It's a big number. Move that decimal point over 6 positions. That's a big number. And even given that big number, because that's how many atoms we're talking about with respect to potassium, when we tally up its weight for the number, look how tiny it is, 10 to the -6 grams. Most balances in the lab can't weigh that much. Yeah, that small, so tiny. The labs in our the balances in most of the labs that we'd be doing in the actual lab, if we were face to face, could go maybe 4 decimal places. That's about it. All right. So, which brings us to, we talked about a special condition, which was STP. Standard temperature and pressure, okay? Under these conditions, and I repeat, only under these conditions, when it is 0 degrees Celsius in 1 atmosphere, okay? Under these conditions, 1 mole of any gas will have Avogadro's number of molecules of that individual gas. So hydrogen, fluorine, ammonia, xenon, and methane at STP, having 1 mole of that gas, will consist of 6.02 times 10 to the 23rd molecules of that gas. Now, obviously, each one of them is going to have a different molar mass. Makes sense, right? Because each one has a different type of atom. So oxygen, hydrogen has a molar mass of 2.02 grams per mole because there's two hydrogen atoms, each one at 1.01, and it's diatomic. So its molar mass is 2.02. And then we have something like xenon gas, which is pretty hefty. It's 131.29 grams per mole. Its molar mass. Of course, xenon is a very big element. Okay, element number 54 is 54 protons, 54 electrons, and the neutrons too. Now, what they all have in common is the following: is that under those conditions, 1 mole of those gas have this new relationship called 22 points, called the molar volume. It is that gas occupies a volume of 22.4 liters per mole. Prior to this, when we were talking about the properties of gases, we couldn't say that. We said that gases don't have a volume, measurable volume. Okay, they occupy the volume, whatever container they have, unlike solids and liquids, that both of those have measurable volumes. Gases did not. However, they do when they are at STP and at 1 atmosphere pressure. Okay, right now it's about 1 atmosphere pressure. Okay, here in Tempe at least. Okay, anyway, so that is what we call the molar volume at STP. And that allows us to do some calculations to actually calculate the volume of gases when we are at STP. Okay, so 22.4 liters per mole is our new ratio that we have now, another additional tool to do calculations. And we can write it in one of those two ways but only at STP, okay? We can write it with 22.4 liters per mole or 1 mole per 22.4 liters. Which one we need simply depends on the question we're being asked, okay? And so, for example, let's do a couple of examples. Here, the question is, what is the volume? So I'm highlighting, identifying what I'm looking for. That is what I'm looking for. And of 1.25 moles of argon gas, okay? Now, obviously well, I won't say obviously, but what I do just out of habit until, I get more comfortable with these reactions, dealing with, are we dealing, it's 39.95 grams. I just make a little side note with the atomic mass of, atomic weight of argon gas, just in case I need it. May not need it, okay, because in this question, there's nothing about grams, so, okay, may not need it. Then I'm at STP. That's to make sure that I can use this relationship. So like we've done before, okay, we set up with, write down what we got, 1.25 moles of argon gas, okay? Obviously, we're gonna have a conversion factor, and we are looking for volume of argon gas. So our units have to end up with liters. And so we are STP. That means that moles has to go in the denominator and liters have to go in the numerator, okay? Because my moles cancel, and I got that properly set up. Okay, so I put in my numbers, 22.4 on top, 1 on the bottom. Okay, units cancel, I end up with that. Now I just do the math. The math's on you. Okay, also note, look at the mathematics of what you are going to calculate. A lot of times, we get in a hurry, type in the number, and then whatever the calculator says, we write that down and not really thinking about the answer. And what I'm asking you to do is, does the answer make sense? Okay, because that will save you a lot of time sometimes when you You might have choices on, it's a multiple choice. It could, one of the choices could be the incorrect answer you might get because maybe you inverted that ratio or did something to that effect. So think about the answer. And what I mean is this: you have 1.25 moles to begin with. You know that in 1 mole, it occupies a volume of 22.4. So you got a quarter more mole, okay? So it just stands to reason that the final number is going to be a little bit more than 22.4 liters, right? That makes sense. So that is what I mean by thinking about what kind of answer you should get. If you get an answer that's much, much less than 22.4, or maybe 3, 4, 5 times that, that should also be a flag for you that maybe I did something wrong in my setup, right? So, and set that up. And again, here we go. So we got 28.0 liters, okay? And it's reasonable because we know that 1 mole occupies 22.4 and about a quarter more gives you about a quarter more volume. So that's a reasonable answer. Second of all, our Sig Figs. Recall that the 22.4 liters is a measurement, okay? It's not an exact number. Therefore, could play a factor in your Sig Figs. We don't forget Sig Figs. Sig Figs, like I stated way back when, we used throughout science. And so we started off with 1.25, which has 3 Sig Figs. And that, by the way, is a measurement because it started out in grams, which is a measurement, then it got converted to moles. Okay, so I got 3 Sig Figs at 1.25 and 3 Sig Figs at 22.4. Our answer should only have 3 Sig Figs. Okay. Okay, the next one. How many moles is 30.4 liters? This time we're being asked how many moles is 30.4 liters of O2 gas at STP. Okay, all right. So I write down what I'm given. O2. I know I got a conversion factor here. I'm looking for moles of O2. Okay. So that means that I need moles unit-wise in the numerator and liters in the denominator. And so I got 1 mole divided by 22.4 liters. Okay. And again, think about your answer. You had starting off at 30.4 liters. You know, then a 1 mole is 22.4, so this number is a little bit greater than 1. I would expect mathematically. Okay, so let's set that up. And sure enough, there you go, 1.36 moles. Okay, so 30.4 liters of oxygen at STP represents 1.36 moles. Okay, now we have slightly different here, okay? Up to this point, you know, earlier I wrote down the atomic weight of argon. I said, hey, just in case I need it. I didn't need it. I didn't need it for the O2, okay? But as a habit, I do that. I just write it down just in case I need it, okay? So, but over here, 1 and 2, there's no mention of grams anywhere, but guess what? Or grams or mass. The next question is asking, what is the mass? So that should indicate to you that maybe I need the molar mass. Second thing, we're looking at chlorine gas. Chlorine gas, tell you, I'm looking at diatomic chlorine, okay? And why is that important? Because I'm going to need the molar mass for that. And it's 35.34, so it is what, 70.90 grams per mole for chlorine gas. If I didn't recognize that, I could have inadvertently just said 35.45 grams, thinking I'm only dealing with the atom, and that's not the case, okay? So I got to get the molar mass. And I'm still at STP. Oh, sorry, somebody had a question. Yeah, no problem. No problem. Yeah, you do what you got to do. Yeah. All right. Yeah, if you guys have, you got to, move on and do what you got to do, hey, feel free. Just, this is all recorded later on. You can catch up with the recording if you want. All right, so I'm looking for mass. So obviously mass, I'm going to have grams in here, and that should flag me to say, okay, I need the molar mass. Okay. And so now I write down what I'm given. I got 4.50 liters of chlorine gas. Okay. Now I need to get to moles of chlorine gas. Okay. I can't go directly from liters to grams. And our common thread is moles. Okay. And so since I'm at STP, I can utilize the 1 mole per 22.4 liters. Okay. At this point, I'm now in moles of chlorine. Moles of chlorine. So having one more factor, which would be the molar mass, setting it up that I'm going to have 70.9 grams in the numerator and 1 mole in the denominator. Okay, check my units here. All my units are canceling out. What I'm left with is grams, which is what the units I'm looking for. Okay, so here's an example of multiple conversion factors where we took a unit of liters, which is not even directly related, and otherwise you might think, well, wait a minute, how can I get to liters to grams? Well, I need conversion factors. And the first factor was the moles, because I knew I got liters of a gas. And the only way I can do anything is I can convert that gas into moles. Okay. And once I'm in moles, I can go in multiple directions here. We're going to have a flow chart here for you to demonstrate that. So I'm in moles of gas now, in chlorine gas. Now I can get to grams using the molar mass. And so what does it look like? Here we go. And so 4.5 liters of chlorine gas at STP will weigh 14.2 grams of chlorine. Okay. And we may not be able to weigh this gas, we don't have the balance, but we can measure volume. Okay. And if we know that if we put it down to 0 degrees in 1 atmosphere, we have a way to measure the volume. Now we know directly how many grams that gas weighs. Okay. The other aspect too, setting that up, you can see that my units cancel out properly, leaving me with grams, which is what I was looking for. Now this is 2 conversion factors, but it's a general guideline that we're going to probably be using on the average, at least 3 conversion factors to get from point A to point B. Okay. Here's the flow chart. Saying when we are in grams and I want to get to volume, whatever volume that is, I can't go that example we just did. But what we just did, we started in volume and went in this direction. We went to grams. Okay. And so this direction, this flow chart goes in both directions. Against a 2-way arrow. And so we just did the volume and went back to grams. But to do that, we had to go to the central moles. That is the unit to get from point A to point B. I could have gone from volume to actual molecules of chlorine gas, but I needed to get to moles either way. If I got grams, I cannot go directly to atoms. I cannot do that. I got to go through moles to get to atoms and vice versa. And so all these directions here is a double arrow, okay? The one in yellow is very important, only at STP. If you're asked a question about a gas to calculate the volume and there isn't a mention of the words, the letters STP, or they mention 0 degrees, 1 atmosphere, okay, it could be one or the other. If they don't do that, then there's nothing you can, there's no, the answer is you can't measure it unless you're under those conditions, okay? And if you have a choice there, so you can't answer, not enough information, that's the one I will pick, but if I'm not at STP. So that's the flow chart here. And in the next chapter, we're gonna add an additional part for this. Right now, we just did the example of dealing with the gas and going from grams, and from the grams, you can go to the atoms and so forth. We'll be doing that. Our conversion factors to go from grams to moles is molar mass, okay? Molar mass, if I have grams and I want to go to moles, I will divide by the molar mass. You look at the examples we just did. If I have moles and I want to get to grams, guess what I do? The converse of that, I multiply, okay? And then the other conversion factor to get us to units of atoms or molecules or units or formula, whatever, is Avogadro's number, 6.02 times 10 to the 23rd units per mole, okay? All right, and here. So here's some examples here. Let's try this. I got a question here. It says, how many grams does 17.35 liters of neon gas mass at STP? Once we know, and then that's the first question, number one, okay? And then the second part says, well, how many atoms does this correspond to, okay? And so we're going from volume in the yellow to grams on the left side. And then the second question says we're going from, we need to figure out the number of atoms. So we can go to the right side. Again, either one, we're gonna get 2 moles before we can do anything. Right, the fact that it's asking for grams also would tell you that maybe you need the atomic weight of neon. And sure enough, you do, you will. So let's set it up. As always, you write down what you're given, and I didn't split my answer there, but your answer will come up to 15.6 grams. But I write down what you're looking for, right? Normally I would say grams of neon as in the question mark. So I write down what I begin with, and now I need my conversion factors. Okay, since I am at STP, I need this first conversion factor to get me out of liters and into moles. Okay. Once I'm in moles, now I can get into where either atoms or I can get into grams. And so here it's neon gas, so I need to figure out the molar mass, which happens to be 20.18, which brings me to the point. Remember this. We talked earlier about Canvas, how Canvas is not the best smart cookie in there as far as software. If you're using atomic weights, please use the atomic weights from our periodic table. Okay, yes, you can go online and you can get an infinite number of atomic weights with multiple numbers, but sometimes they're a little bit different, a subtle difference. And then when you use those in your calculations, you plug that number in, and maybe the answer, for example, is x.18, and you calculate x.19. Well, Canvas is basing its answer on the periodic table we have, and the 0.18 would be the correct answer. And even though you write down 0.19, it's reasonable, it would be considered incorrect. So to save time, I will give you that credit, but to save time, just use our atomic weights, okay? And so here, 17.35 grams of neon gas at STP will weigh 15.6 grams, okay? And notice how we went unit-wise. We went from liters to grams, okay? And the only way we can do that is to a common unit, which was moles. We have multiple multiple conversion factors here, but those two conversion factors had in common the unit moles. Okay, second part. Here, the second was how many atoms does it correspond to? So again, we write down what we're given. Obviously, we're going to need the first, same first conversion factor. Okay, 1 mole per 22.4 liters. We're at STP, and the only difference here, we're using Avogadro's number to get us to the number of atoms. Okay, check the units out. I can't overemphasize of keeping track of the units, because definitely if you do that, you 100% of the time set that problem up properly. And now the rest is up to you, and that's, plugging in the right number in the calculator. And so for 17.35 liters of neon gas, that represents 4.66 times 10 to the 23rd atoms. Quite a bit of atoms, right? And so these two examples that we just did is that flow chart there. Okay, we went from the yellow to the blue in grams, and then we went again from the yellow, but we went to the right for atoms. But either way, we had to go through moles. All right. Any questions about this example? We're going to do a few more here in the bit. Okay. Yeah, flow chart, very, very important. Now, what we have here now is density, and we talked about density before. Density, again, ladies and gentlemen, is simply a ratio, right? We talked about this earlier, way back, where it's a ratio of the mass of whatever matter you're looking at divided by the volume it occupies, okay? Now, we have an alternative way to calculate mass. Before, we had to actually weigh out the material if we needed density, and then calculate, determine the volume, and then just take that ratio, divide it, and you're good to go. Well, here we're dealing with gases, and we have a kind of a shorthand way to calculate what we call the density, okay? And we take the molar mass and we divide it by the molar volume, okay? And so let's just take the units of molar mass, because the units of molar mass are grams per mole, correct? And we divide by the molar mass, which is liters per mole. So we are dividing fractions, right? It's simply like, like if I take 1/3 and I divide that by 1/2, what do I do with that fraction denominator? I invert it and then I multiply, right? And so now this becomes 2/3, right? Well, we're doing the same here where we got grams per mole, okay? And we invert the denominator unit-wise, and now it's moles per liter. The moles cancel, and guess what we had left over? Unit-wise, grams per liter. And those are the units of density. And so simply by knowing the molar mass of the gas and being at STP at 0 degrees and 1 atmosphere, because we know the molar mass is 22.4 liters, we can determine what the density is for a gas at STP. And so for ammonia, the molar mass is, we have to add everything up, right? 1 nitrogen, 3 hydrogens, that adds up to 17.04 grams per mole. That is the molar mass for ammonia, NH3. And we divide by the molar volume, okay, because we are at STP. And therefore, our density for this ammonia gas at STP is 0.761 grams per liter. Okay, grams per liter. Now, I know the units that we worked with before were grams per cc, grams per cubic centimeter, or grams per milliliter. We can convert this to those units, but most of the time when we're dealing with gases at STP, we just leave them as grams per liter. Okay. All right. Percent composition. We did an exercise a while back where we gave you some formulas and we asked, okay, how many atoms of each one do you have in this particular formula? Okay. And that was for a purpose, because now what we're going to do is show you why we did that. Here, what we're going to do is determine or calculate the percent composition. And that is the mass percent of each element in a compound. And it's pretty straightforward. You just add up, you need the molar mass of the compound, because that is this is a percentage, so it's part over the whole. The whole represents the molar mass, and the part represents the contribution of every particular atom that's in that compound. And so we've calculated the molar mass of water before, and that was 18.02, okay? And what we did was tally up the hydrogens and the oxygens to give us that number. We know that hydrogen, there's 2 of them, so that's a total of 2.02 grams per mole. There's a typo here. These are not grams of hydrogen, is grams per mole. So make note of that, okay? The units were the units of the atomic weights, which are not grams, or grams per mole. And so if we take 2.02 divided by the molar mass times 100, you get 11.2% hydrogen, okay? Hydrogen in water. If we do the same thing with oxygen, it brings in 16 grams per mole. It represents 88.79% oxygen. And so if you were to take a water sample and do an analysis on it, you will find that it would consist of 11.2% hydrogen and 88.79% oxygen with the formula of H2O. And that would be true whether that water came from your sink or out in space someplace, H2O. That is the composition, the percent composition for water. Okay. So let's try one of the problems, okay? So it says here, let's find the percent composition for TNT. Anybody know what TNT is by chance? There's another common name given to it. Anybody know? Dynamite. Okay. TNT comes from the name, its chemical name is trinitrotoluene. So they took the T from tri, the N from nitro, and the T from toluene. Okay. And kind of side note, I know it's not we're not dealing with organic chemistry here, but some students would like to know the structure. TNT has a 6-membered ring, FYI, and then there's a carbon on the side, and then it has 3 nitro groups, hence trinitrotoluene. The fascinating thing about this is putting the first nitro group is not bad, but putting the second one is tough when you're trying to make these synthesize it. And it's extremely challenging. Side note, another side note, I throw in side notes occasionally. Anybody by chance know who created TNT? Let me give you a hint. There's a prize that is given annually for medicine, for chemistry, for physics, for literature, for peace. And
Was it Wilbrand?
Wilbrand? No, Nobel.
Oh, yeah.
Yeah, Nobel Prize. Actually, when he created TNT, it just made him a mint of money. Obviously, it was used for multiple reasons. And so he just made a man of money. And so he created the foundation, which distributes the Nobel Prize every year. So that prize came from a big boom, so to speak. All right. So what we do here is we count the atoms. We got 7. It tells you there's 7 carbons, 5 hydrogens. We got 3 nitrogens. Remember, in parentheses, that's a nitro group. We call nitro. And 3 of them, and there's 6 oxygens. Okay. And so we start up our little grocery list, if you will. So we got 7 carbons at 12.01. That's a total of 84, 0.07 grams per mole. There's 5 hydrogens at 1.05. It's a total of 5.05. Nitrogens, 3 of them at 1401 for each one. That's 42.03. And oxygens are 6 at 16. That's 96.00. And that gives us a total molar mass of 227.15 grams per mole. Okay. Now we just simply go through each one. The contribution of carbon was 84.07 divided by the molar mass times 100. Okay. That's 37.1%. The hydrogen represents 22.2%. Nitrogen's 18.5%, and then following at the end at 42.26%. I believe it is. Tough time on the screen. Yeah, 42.26%. And in the quote real world, so to speak, as an organic chemist, we did this all the time. We make a new compound, synthesize it, and then clean it up, purify it, and then run it through our instrumentation that we had to kind of determine what kind of structure we had, define the structure, and then we shoot it off for analysis and to figure out the percent composition of carbon and hydrogen, nitrogen, and so forth. And if you were right, that numbers come in just like that. So that was a good thing. Okay, so try this one at home. We can bring it next Friday if you have trouble with it, but the question is, how many liters will 3.425 grams of carbon dioxide gas occupy at STP? Okay. And you should come up with an answer of 1.74. The second attempt is how many molecules are in 3.425 grams of carbon dioxide? Same amount of carbon dioxide. So basically convert that information into the actual molecules. And then working it backwards, so to speak, if you had 3.0 times 10 to the 15 molecules of carbon dioxide, how much would that weigh? And you should come up with 2.2 times 10 to the -7 grams. Okay, very small amount weight for that humongous number of molecules of carbon dioxide. Again, give you some perspective as to how small these atoms are. All right, so try these at home. See if you come up with those answers. And if you have a challenge with it, then we'll definitely, this is a good time to bring it in on Friday, because next Friday we'll probably just do chapter 14. All right, and that, ladies and gentlemen, brings us to the end of chapter 12. Congratulations. A few more to go. All right. Let me continue with any questions about chapter 12. All right. Any questions in general for anything else before we proceed? Again, the exams are chapters 10, 11, and 12. So we're done with those. And this brings us into what is called stoichiometry. Okay. And that's related. This is related to the coefficients that we have when we were balancing chemical reactions. Remember, I stated when we balanced it, we had a number in front of the reactants. If there's no number, it's understood to be 1. And so we had this ratio of maybe a 1-to-1 relationship between reactants, or 1 or 2-to-3, or 1-to-3, or 1-to-4, whatever the case may be, depending on the reaction. And that's reactants, but we also have that same relationship with the products, with reactants to the products. Okay, and those are the coefficients that we're going to be utilizing to help us to do calculations, because eventually we're going to get into a scenario that we are given, A plus B reacts to gives us C plus D, and maybe this is 2 of those, maybe 3 of these. And you might be asked the question, all right, if I start off with 10 grams of A, can you tell me how many grams of D are you going to make? Okay. Or you might be asked, I need 50 grams of C. Okay. Well, if I do that, how many grams of B do I need? Okay. And to answer that question is going to be related to, 1, the molar mass. So we need to calculate the molar mass of any of these species that we're going to be using. Okay. And then from that, looking at the ratio, which is the coefficient that balances the chemical reaction, to get us from grams of, let's say, C to eventually grams of B. And you can see, but based on what we've been doing so far, in order to do that, I got to go through moles. Okay, moles is the connecting factor between all of these reactants and products. Well, to mole or not to mole, as they say. All right. So let's take a look at this general reaction. We got nitrogen monoxide in the presence of oxygen to give you nitrogen dioxide. Now notice, that could have been how it was written out for you to look at, and then taking what I just stated, take that information and convert it into a chemical reaction, okay? And then from that, once we've converted it into the chemical reaction, knowing the physical states, putting that in there, knowing who's diatomic, maybe even knowing who's solid, okay, and which ones are liquids and so forth. Okay, and so then once we do that, then we balance it. And recall that of the 6 type of reactions, we had a stepwise way to calculate or to do the balancing. Others were simply, you have to do, they're small enough that you can do a little trial and error, playing with the numbers, the coefficients, such that everybody's balanced. Okay, so this one is balanced. I got 2 nitrogens in the left, 2 on the right. I got 4 oxygens on the left and 4 on the right. So everybody's happy. Now, on my relationship between the reactants, I could state as follows. I could say that I need 2 molecules of NO to react with 1 molecule of oxygen. And when that occurs, I will get 2 molecules of my product, okay? So that is my ratio. That is my ratio. So anything I do, I can up the ratio or even bring it down, but that ratio will be maintained. So if I go through and multiply everything by 5, it's the same thing as saying 10 molecules of NO require 5 molecules of oxygen, which will then give me 10 molecules of my product. That ratio is the same. 10 over 5 is the same thing as 2 over 1, right? Same thing. But generally, we don't talk about molecules. What we utilize is the term moles. So when I read this reaction, I say, okay, 2 moles of NO require 1 mole of oxygen to give me 2 moles of my product. And if I need an actual number, each mole is 6.02 times 10 to the 23rd. But in this case, this is times 2 because I got 2 of them. And the oxygen is 6.02 times 10 to the 23rd molecules of oxygen, which then will give me 2 molecules of 6.02 times 10 to the 23rd molecules of nitrogen dioxide, okay? So we talk in terms of moles rather than molecules. All right, so let's look at the second one. We have nitrogen in the presence of hydrogen gas. You got nitrogen gas in the presence of hydrogen gas reacting to give us ammonia, NH3, okay? And so here we can talk about molecules, 1 molecule per 3 molecules of hydrogen to give us 2 molecules of ammonia, okay? Or we talk about 1 mole of nitrogen requires 3 moles of hydrogen to give us 2 moles of ammonia, okay? And so the relationship between the stoichiometric relationship between nitrogen and hydrogen is a 1 to 3, okay? Remember, it's understood to be a 1 there, 1 nitrogen per 3 hydrogens, which if I need that ratio written out, I can write it like this, or I can put 3 hydrogens, 1 nitrogen this way. Which one I need depends on the question. There's also the relationship between the hydrogen and the product, which is a 3 to 2. You can see that. And between the nitrogen and ammonia, which is a 1 to 2. So we keep track of all these ratios because we could be asked any multiple questions. All right, so coefficients gives us molecules, or more accurately, the mole ratios. Okay. And let's take a look at this reaction here. We have 1 mole of iron 3 oxide reacting with 3 moles of carbon monoxide to give us 2 moles of iron and 3 moles of carbon dioxide. Okay, that's how we interpret that balanced chemical reaction. Are we balanced? Yeah, do a quick check. I got 2 irons on the left, 2 on the right. That's good to go. 3 carbons on the left, 3 on the right. That's good. I got a total of 6 oxygens on the left and 6 oxygens on the right. Definitely we're good to go. Everybody's balanced. So now once this is balanced, I have ratios that I could utilize. If I'm looking at just reactants, I can write that relationship, that stoichiometric relationship of 1 mole of iron 3 oxide over 3 moles of carbon monoxide. Or I can write it in this other way, okay? With 3 carbon monoxide and 1 iron 3 oxide. What I have is essentially quite a number of relationships. And then I got my other one. I'll keep these in the same color. So I got this relationship here going, okay? And then I have between iron and carbon monoxide, I got this relationship right here. It's listed here. I can write it in one way or invert it. So I got, and every arrow here represents 2 ratios. So now I got a carbon monoxide and carbon dioxide relationship. Okay, so I got 1 here, 2 here, 3 here. I got the iron 3 oxide and the iron. That's 4. And then the iron with the carbon dioxide, that's 5. And then I even between the products between the iron and the carbon dioxide, that's 6. So I got a total of 6 stoichiometric relationships, and each one has a ratio. So that's a total of 12 ratios that I can utilize depending on what I'm being asked question-wise, okay? Now, with respect to these type of questions, if let's do an example, okay? All right, the first question says, how many moles of iron? Okay, so I go up here and I mark my equation so I know what's being asked. So I got how many moles of iron can be formed from 10.2 moles of carbon monoxide. Okay, so 10.2 moles. So I'm being asked, the only thing that I need to worry about is between iron and carbon monoxide. I do not need to be concerned about the other participants in the chemical reaction, only the ones that are being asked in the question. Okay. All right. So as any other problem, conversion factor, we write down what we're given, 10.2 moles of carbon dioxide. Okay. Obviously, I'm going to need a factor here. And what am I looking for? I'm looking for moles of iron. That's what I'm looking for. So that tells me that CO2 must be in the denominator, and obviously iron must be in the numerator. Okay. And so iron is a 2, carbon monoxide is a 3, the coefficient. So I got it set up properly. So now the math is on you. At this point, you can see that I end up with units of moles of iron, which is what the question asked for. And so now I'm given carbon monoxide. I'm trying to relate that to iron. I'm going from an apple to an orange, so to speak, but I'm using my common factor. And for that analogy, it's fruit, right? Here I'm going from carbon monoxide to iron, and I'm using the common factor of moles. So I got to get the moles of carbon monoxide and convert that to moles of iron, which is taken from the relationship of the balanced chemical reaction. All right, so you can see there that moles of carbon monoxide cancel, leaving me with moles of iron. This 2 to 3 ratio comes from the balanced chemical equation. So I have 2/3 that amount of 10.2, which is 6.80. Okay, yeah, 6.80 moles of iron are formed if I start off with 10.2 moles of carbon monoxide. And like I said, when I just showed you, I'm only concerned about these two. Everybody else, not concerned about. You just assume that there's enough iron 3 oxide to react completely to get all this carbon monoxide to react. Okay. Now, I state that because I've seen problems that have been shown that include iron 3 oxide and include carbon dioxide. And I'm kind of perplexed because the question is only asking about iron and carbon monoxide. And it's not asking anything about iron 3 oxide or carbon dioxide. Okay. All right. Let's look at the second one. The second one says, how many moles of iron 3 oxide, okay, so it's this guy, are needed to form 17 moles of carbon dioxide, this one. So our relationship that we're concerned about is between the iron 3 oxide and carbon dioxide. And here's an example where you're being asked, okay, I need, for whatever reason, 17 moles of carbon dioxide. Can you tell me how many moles of iron 3 oxide do I need to begin with? And this is typical in the real world, you know, in the lab itself, small quantities, but if you're in an industrial plant, you know, it could be 17. You might come up and say, okay, in the lab, I need 17 grams of it. But in the industrial plant, I need 17 metric tons of it. Regardless if it's metric tons or grams, that ratio, the calculation is still the same. Okay. All right. So as always, how many moles? We write down what we're given. We got 17 moles carbon dioxide. Okay. We are looking for moles of iron 3 oxide. And so therefore we have 3 CO2 in the denominator, 1 iron 3 oxide in the numerator. We want CO2 to cancel, leaving us with iron 3 oxide unit-wise. Okay. Plug it in, you should end up with 5.7 moles of iron 3 oxide. Are needed, 5.7 moles of iron 3 oxide are needed to generate 17 moles of carbon dioxide. Now keep this in mind. We're doing baby steps here. We're working with the moles to get you into the mole step, because the next step is this. You know that we can go from moles to grams, right? Using the molar mass. So right now we're in the moles, but it's just a real simple step now to get from 2 grams, because in the lab, I cannot weigh out 5.7 moles of iron 3 oxide. Our balances don't do that. Our balances work in units of grams. So I need to convert that 5.7 moles of iron 3 oxide to grams. And that is where the molar mass will come into play to calculate how many grams that corresponds to. So hopefully you can see how we're going to start with. If I start with grams of A, how many grams of B do I need or I make in some reaction? Okay. So if we balance this reaction, which we have sulfur dioxide in the presence of oxygen, require 2 moles. With 2 moles of sulfur dioxide, 1 mole of oxygen yield 2 moles of sulfur trioxide. Okay. Now we're still stuck with the moles right now. We'll graduate here in a little bit. Okay. And so what I need is simple. It's real straightforward as far as I want to get from moles of oxygen. Okay. How many moles of sulfur dioxide would form if I start off with moles of specifically 0.065 moles of oxygen? All right. So my only concern is between these two. Don't worry about the SO2 question. Doesn't even ask anything about SO2. Okay. And so that is what we're given. Then we have the stoichiometric relationship between sulfur trioxide and oxygen, which is a 2-to-1. And so I need twice that amount. 0.33 moles of sulfur trioxide will form, I shouldn't say that I need twice the amount. It's how many moles will form if I start off with 0.165. Okay. All right. The next one was how many moles. Let me clear this up here real quick. How many moles of sulfur dioxide are needed to make 0.042 moles of sulfur trioxide? And so now we're looking at just those, the relationship between those two. Not worry about the oxygen at all. Okay. Notice it's a 1-to-1 or a 2-to-2. And, you know, until you get comfortable with that, seeing that relationship, go ahead and put the coefficients in. Okay, you can see mathematically they cancel out. So it's a 1-to-1 relationship. My moles of sulfur trioxide cancel out, leaving me with moles of sulfur dioxide, which is what is being asked. And so it turns out that I need the same amount, this same number of moles pertain to the sulfur dioxide. Okay. So if I need to make 0.042 moles of sulfur trioxide, I need to measure out the same moles of sulfur dioxide. All right, so this particular mole flow chart kind of puts it all together, okay? It's very similar to the other flow chart we dealt with when we were working with SDP. In a bit, we're going to combine those two. And you have one flow chart that will allow you at a glance to help you out to get from point A to point B. So if we look at the problem here, the flow chart, I should say, the stoichiometry relationship. 1, we're going to need the molar mass of your reactants. 2, we're going to need the mole ratio from the balanced chemical reaction of whatever relationship you're trying to determine. So from A to B, you got to find the mole ratio between A and B. Once we that, and then at the end, you're going to need the molar mass of B. So here we start off with A. Over here, we end up with B. Okay. All right. And they're all connected. The only way we can get in that direction is through moles. So once I have the grams given, and I just need the molar mass of A, okay, which I divide by the molar mass. Guess what? I'm dividing by the molar mass to give me the moles of what I'm given. And then from the balanced chemical reaction, I'm able to determine how many moles of what I'm looking for. In this case, to be the moles of B. Knowing the molar mass of B, I will now get the grams because I'm going to multiply by the molar mass to get me 2 grams. Okay. And so again, I cannot go directly in that route. I have to go through moles and the mole ratio and the molar mass to get from point A to point B. So that corresponds to basically, if you think about it, 3 conversion factors. The molar mass here, the mole ratio here, and the molar mass right here. Because if I start off with grams of A and I want to get to grams of B. See how that is in general terms? Okay. Okay. Well, let's take a look at this reaction here. And there's 2 questions to it. Okay. First question says, well, let's look at the reaction before I go any further. It is the reaction of, I'm going to put it in words, and then there's the reaction. The reaction of iron to oxide in the presence of aluminum yields elemental iron and aluminum oxide. Okay. So that sentence would then could be used to be converted into this equation and then balanced. Okay. And then obviously everybody hears solid. So we're not even talking about aqueous, but everybody hears solid. Aluminum oxide is an abrasive. You might find it a lot in sandpaper and stuff. Sometimes some of the, what do you call those things you use to do your fingernails? I don't know, sandpaper on a bar or whatever. And it's a lot of abrasive material, aluminum oxide. All right, let's double check. I always double check. I'm given an equation. You know, how do I know that you make a typo and it's not balanced? So let's check it out, make sure it's balanced. I got 3 irons on the left, 3 on the right. I'm good. 2 aluminum on the left, 2 on the right. That's good. 3 oxygens on the left, 3 on the right. Okay, we're good. Okay, now they're asking you here, calculate the mass of iron 3 oxide needed to react completely with 5.5 grams of aluminum. Okay, and so iron 2 oxide, we're talking about this guy, and aluminum. Okay, and if I start off with 5.5 grams of aluminum, how many grams of iron 3 oxide do I need is the question. That is what's being asked. Don't care about what's going on down there, only between the 2 reactants. And that ratio is a 2-to-3 ratio. Okay. Now the second question says calculate the mass of aluminum oxide. Let me clear this up. We want to calculate the mass of aluminum oxide, so it'll be X grams of aluminum oxide produced when 10.025 grams of aluminum reacted completely. So again, our relationship that we're concerned about is simply between aluminum and aluminum oxide. Don't care about iron or the iron 2 oxide. Okay. The fact that we start off with grams should also tell you that I'm going to need molar mass. So I would start, writing down the molar mass of the parties that are going to be involved in the chemical reaction here. Okay. All right. So we have identified what's going on and what we're trying to calculate. So let's do the first one. All right, so our relationship here is between the iron 2 oxide and the aluminum. That's what we care about only. So we start off with 5.5 grams of aluminum. Step number 1, we need to convert those grams into moles. Okay, and so aluminum is an element, and we simply go to the periodic table and we determine the atomic weight, which is 26.98 grams per mole. And we write it with grams in the denominator. Why is that? Because we want grams to cancel and go away. Do we not? Yes, we do. At this point, our calculation, if we were to stop it, would give us moles of aluminum. Okay, but we're not stopping at that point. We need to continue. So we're going to eventually get to, we need to get to grams of iron 2 oxide. So the next relationship is between the iron 2 oxide and aluminum, which happens to be a 3:2 ratio. Okay, note the units. Yeah, that's why important. We put units on it. Notice all the units cancel, and what's left behind at this point, and again, if we stop the calculation right here, now we are in moles of iron 3 oxide. It's like saying I started off in A, grams of A, now I am in moles of B. But we're not done, okay? Because we need eventually get to grams of B. In this case, it turns out to be iron 2 oxide. So we need the molar mass of iron 2 oxide. Notice that my units, always setting them up properly, leaving me behind unit-wise only grams of iron 3 oxide, which is what the question asked for. Okay. Now I simply do the math. A mathematical, I may have stated this before, check your calculator. Every calculator is a little bit different. Most modern calculators should know the priority with respect to mathematical function, to do it. So what I'm saying is if you take the 5.55 divided by 26.98 and then hit the multiply by 2 and divide by 2, multiply by 3, and then hit the divide by 2, and then multiply by 71.85, your calculator understands it, does it properly. Just to double check, take the 5.55 divided by 26.9, hit the equal. Then multiply by 3 and hit the equal. Divide by 2, hit the equal. And then finally multiply by 71.85 and hit the equal. Check your answer. And if you did it both ways and they're both the same answer, then your calculator understands the priority rules as far as multiplying and keeping track of what you did. Okay, so you might want to double check. All right, now the second part of the question was we start off with 10.25 grams of aluminum, and we want to figure out how much aluminum oxide can be created if you begin with 10.25 grams of aluminum, which means that we're only concerned about, again, aluminum and aluminum oxide. So there's plenty of iron 3 oxide to be created. And yes, we're going to be making some iron, but we're not concerned about that. We're only concerned about the aluminum oxide. based on the question that we were asked. So as always, we got to convert the grams into moles. Okay. And then from the balanced chemical equation, we utilize the mole ratio to get us 2 moles of aluminum oxide, because it's a 1:2 ratio. Okay. And then finally, the molar mass of aluminum oxide will get us into grams of aluminum oxide. Check your units. Grams of aluminum cancel out with the first conversion factor to give me moles of aluminum. The second conversion factor gives us moles of aluminum oxide. And then the final one gets us into what we're looking for, which is grams of aluminum oxide. And so I start off with 10.25 grams of aluminum and sufficient iron 2 oxide. Then I should generate the following amount of aluminum oxide, 19.37 grams of aluminum oxide. Okay. All right. So here's the flow chart I just was talking about. We had done the volume, the ones in yellow previously, and then we just finished some examples of grams given and looking for grams defined, so you can put the whole thing together. Okay, so to get anywhere from here to here, I need moles, everything moles. This comes from the balanced chemical equation. To get, we need the molar mass of what we are given and the molar mass of what we're looking for to get to grams. Now, only at STP, we can go in this direction, okay? Only at STP. Now, this is a 2-way arrow, so you can go in both directions, depending on what you're doing, okay? And that flow chart there just helps you run through the calculations and set them up properly. Okay. All right, let's do a quick 10 wait, what time is it? I got 2:32. Let's do a quick 15-minute break. Right. And okay. I'm back. Let's break down this reaction here. It's telling to write and balance the reaction of hydrochloric acid and solid cobalt. Excuse me. Then they give you some additional information in that nickel, excuse me, I got nickel in the brain, cobalt will be in the +2 oxidation state. They have to give you that information because if you recall, there's only 16 metals that have a constant oxidation state, and nickel is not one of them. So that's why you're given that information. All right, now you might say, all right, so let's write down what we are given, and that's cobalt plus HCl, which is aqueous. And we know cobalt is a solid. So we got to write down, you might think, oh, wait a minute, what are the products here? Okay, so does this look familiar, this reaction? Hopefully it does. If you look at this, we have a metal interacting with which normally would be another metal in the salt form. Okay, remember the single replacement reactions? But if you recall, on the we got cobalt on the activity series. I'm not going to. You can look that up, but you'll see that. Remember, I stated that the activity series is relative to the reactivity of hydrogen. Okay, and so here we are comparing the reactivity. Remember the steps. We compare which metal is more reactive, which is more active. In this case, H is really, we're comparing cobalt and hydrogen. So from the activity series, cobalt is a lot more reactive than hydrogen. Okay. And the second question asks, is the most reactive metal in salt form or ionic form? And the answer is no. Therefore, reaction proceeds. So we're going to exchange places with the cobalt in elemental form is now going to become cobalt in ionic form, and they're telling us it will be specifically in the +2 form. Hydrogen, which is in the ionic form, now goes to hydrogen in the elemental form, which, as we hopefully know by now, that is hydrogen gas. Okay. Recall, I also mentioned that between magnesium and up to let me look at it, make sure, lead, okay, those metals require an acid to react, okay, because they're a lot more reactive than hydrogen. Whereas the ones that were bold, they reacted with water spontaneously. They had a totally different product. So anything above hydrogen, metal-wise, would not react with an acid like these would. And the acid, when the acid reacts with that metal, one of the products is hydrogen gas. It stands to reason because hydrogen is in the form of H+, the proton here. It's ionic, okay? So it gets converted back to elemental because the cobalt gets converted to ionic. And the chlorides, we know that there are -1. And so therefore our products should be cobalt to chlorides, okay? And furthermore, cobalt chloride, what physical state that would be? Now we tap into the solubility rules. So see how we're using everybody here? We tap into solubility rules and you see that the chlorides are soluble. All chlorides are soluble except only 3. Silver, mercury, and lead, of which cobalt is not one of them. So cobalt chloride is soluble. H2 is gas. HCl is aqueous, that's given. Okay. So let me erase a little bit. Then we're going to do is balance it. All right, so any multiple ways you can try here. We got 2 hydrogens on the right. What if we put 2 hydrogens on the left? Excuse me. Yeah, 2 hydrogens were good. That kicks up my chlorides, my CLs to 2, which works out fine because we got 2 CLs on the left and the right. 1 cobalt on both sides, we're good to go. Looks like it's balanced. Okay. And so let's clear my mess and we'll bring in the better one. So there's our formula. Okay. So we broke it down stepwise, right? Taking all the information we're given and just wrote the equation. Then we put the physical states in, then we balanced it. Okay. So now we can do any type of calculation from this reaction. Okay. And here is the first calculation. They want to know is this: how many liters of gas? And you're like, whoa, wait, no gas. Well, of course, hydrogen. Okay. How many liters of gas will form if you start off with 5 grams of cobalt? And so that's our only concern between cobalt and hydrogen gas. Okay, so we write down what we're given, and that's 5 grams of cobalt. Okay, let me clean up my mess. 5 grams of cobalt, and obviously we're going to need the atomic weight of cobalt. And that we get from the periodic table. and that is 58.93 grams of cobalt per mole of cobalt. And we write it with grams in the numerator because we want grams to cancel. We are at STP. I forgot to mention that. The fact that we're in STP, we can utilize this relationship, 22.4 liters per mole. Okay, so you keep that in mind. So right now, we are in moles of cobalt, and we're trying to figure out how many milliliters of gas we have. So now we have to go to the stoichiometric relationship between the cobalt and the hydrogen, which is a 1-to-1 relationship, okay? And keeping track of canceling my units, we have now converted from grams of cobalt at this point to moles of hydrogen. So we have in essence gone from apples to oranges almost, because eventually we want grams of oranges. And here we need one more step, okay? Because they asked us to calculate how many liters. Now, since we're at STP, all we need to do is to add the 22.4 liter per mole relationship. And now we can calculate that. If you start off with 5.0 grams of cobalt and sufficient amount of hydrochloric acid, your reaction proceeds, okay? And when you're done with the reaction and you were measuring the gas that was being created, you would have 1.90 liters of hydrogen gas. That is what our calculation tells us that we should get. And we talk about this, you know, what we calculate how much product we're going to get. We call this a theoretical yield, because that's what we get theoretically. But in reality, not all reactions go to 100% completion. And we generally end up doing what's called a percent yield. And that's basically just the actual amount we actually get from the reaction divided by this theoretical yield times 100. And ideally, you want to be, you know, close to 90, 80%, but you'd be surprised that most of the time we're in the 30, 40% yield, okay, for multiple reasons. All right, so let's clear my mess. Second question, same reaction, okay? If 2.374 liters of hydrogen gas were formed, so now they're telling you, all right, you ran the reaction and you were to measure that quantity of hydrogen gas, how many grams of hydrochloric acid reacted? So our relationship is between the hydrochloric acid and the hydrogen gas. Don't care about the others, okay? Of course, it looks like we want grams of hydrochloric acid, so it looks like we're going to need the molar mass of hydrochloric acid, so that should be 36.45. The chlorides are, yeah, 35.45, and oh, that should be 36.46. 36.46 grams per mole for HCl. I forgot the hydrogen is 1.01. All right, so we're going to need that. So let's set it up. As always, we write down what we are given, 2.374 liters of hydrogen gas. We're still at STP. And so from there, we can use the 22.4 liter per mole relationship, obviously with liters in the numerator, because we want those to cancel. And that will give us moles of hydrogen, okay? Moles of hydrogen. The second factor converts us to moles of hydrogen to moles of hydrochloric acid, HCl. And since we're looking for grams, then at this point, we just simply use the molar mass for HCl, which is 36.46, okay? Chloride's 35.45, hydrogen's 1.01, that is 36.46. And then once I got all those set up, double check your units, okay? Liters, HCl cancel, moles HCl cancel, leaving me with grams of HCl with respect to the units, which is what I was asked to calculate, Okay. Now it's a matter of plugging the numbers into your calculator, and you should end up with 7.72 grams of hydrochloric acid. Now you might ask yourself, well, wait a minute. I got 3 Sig Figs here, but I began with 4 Sig Figs, right? So what's the deal here? Well, we know that these numbers are exact, and I said the molar mass, atomic weights are never used because they come from whole numbers, average weighted average of whole numbers, so that infinite number of Sig Figs. So we don't use those for Sig Figs. But then our conversion factor of 22.4 liters per mole, I said that's a measurement. So that could play a role in your Sig Figs. And sure enough, here's an example. I got 3 Sig Figs right here. So your answer should be no more accurate than the least accurate number in your calculations, which is the 22.4. So our answer is 7.72 grams of hydrochloric acid reacted to generate 2.374 liters of hydrogen gas. Okay. All right, here's another one. Hydrochloric gas. Now notice in that this would be called. Here's the difference. It's really crazy. HCl that we just use, HCl aqueous, is hydrochloric acid. When it's an aqueous solution, it's called hydrochloric acid. When it's a gas and not an aqueous solution, it's called hydrogen chloride. Hydrogen chloride, excuse me. Okay. Not hydrochloric acid. All right, so HCl gas plus oxygen produces chlorine gas and water vapor. That's some crazy reaction. HCl plus oxygen reacts to give us Cl2, chlorine gas, and water, H2O. Okay. Everybody is in the vapor phase because we know we know oxygen is a gas, chlorine is a gas, and they're telling us HCl is a gas. Okay, so everybody is in the gas phase. So we wrote the reaction, and now we got to balance it. Okay, we're just working through it. Anybody have an idea how I can balance this reaction? What can I do to balance it? Because I'm not balanced. I have 2 hydrogens on the right, 1 on the left. I got one Cl on the left, 2 on the right, 2 oxygens on the left, 1 on the right. I'm not balanced. Excuse my little one in the background. She's very vocal. Any suggestions? No, well, what about? All right, well, okay, let's break it down. Let's try this first. Let's see if this works. If it don't, we'll try something else. All right, we got 2 hydrogens on the right. And if we put a 2 in HCl, that will balance my hydrogens, correct? And on both sides, and will balance my Cls. I got 2 Cls on the left, 2 on the right. So that is balanced. Those guys are balanced. However, it kind of messes up my oxygens here. So what if, because now I got 2 on the left, 1 on the right. All right, what if I put a 2 in front of water? That balance out my oxygen. However, that kicks up my hydrogens to 4 now, right? So if I change this to 4, that will balance my hydrogens. My oxygens are balanced, but my Cls now go up to 4. So now, hey, it worked out. I can put a 2 here, and I think I'm balanced. What do you think? 4 hydrogens in the left, 4 on the right. 4 chlorides in the left, 4 on the right. 2 oxygens in the left, 2 on the right. Guess what? I am balanced. Okay. So let's do this one. All right. That worked out okay. All right, so now we write down where we're given. It says we have how many liters of chlorine gas? How many liters of chlorine gas can be formed if you have 3 liters of oxygen? Okay. This is not too good of a reaction. That's pretty hazardous, chlorine gas. All right, so we write down we're given 3 liters of oxygen. Okay, obviously we are at STP. They're telling us STP, so we can convert the liters of oxygen to moles of oxygen. Okay, now then we use the stoichiometric relationship between the chlorine and oxygen, which is a 2 to 1. Okay, and then finally that puts us into moles of chlorine. And then we went to liters of chlorine. So check my units here. Liters are canceling. Moles of chlorine, moles cancel. I got liters of unit-wise left. And so that, after doing the math, becomes 6 liters of chlorine gas. So if I use 3 liters of oxygen, I will make 6 liters of chlorine gas. All right, now do you see here, we got 3 conversion factors. Can you see where we can maybe simplify this relationship a little bit? Is there anything we can do? Look at the numbers. Do not the 22.4 liters cancel each other out? Yeah, these 2 cancel out right away. And so when you are dealing with all gases, okay, and you are at STP, you don't really need that conversion factor if you're going from volume to volume, okay? All you need to do is have the stoichiometric relationship or the balanced chemical equation to get you from point A to point B. And that is only if you're at STP and only obviously if you're dealing with gases. Okay, but until you're comfortable with that, do by all means include all of the conversion factors. Okay. All right. So try this at home. This would be good for bringing back next Friday. We can talk about it if you can work it out. But the question is going to take this, convert it to a chemical equation, and I'll show you what I got, and then you can I wouldn't copy what I'm going to show you here, but just copy what you need to determine, and then really try it at home in earnest. And then next Friday you have a question about it, bring it in. We can definitely take some time to work the problem. So here it's telling you that carbon reacts with oxygen gas to form carbon monoxide. Okay. How many liters of carbon monoxide at STP can be made from 15 grams of carbon? Okay. And then the first question, and then the second one, if again, how many liters of carbon monoxide can be formed at STP from 20 liters of oxygen? Okay, so one starting with carbon, and the other one starting with liters of oxygen. And there's the equation. You should come up with 28.0 liters of carbon monoxide for the first part and 40.0 liters for the second part of the equation. But first try, please try without the answer there. Okay. So let's kind of summarize a little bit. We started with the elements, and from the elements we started making compounds, either ionic and or covalent compounds, okay? From these compounds, we started reacting with them with each other, and we talked about balancing these reactions. From the balanced chemical reactions, we come up with the stoichiometric ratio that we need so that we can do calculations of either reactants or products that are based on these ratios, and we can give answers in terms of either moles, grams, or liters if you are at STP, okay? If you are at STP. And so this flow chart, well, if you keep that nearby and get comfortable with its reactions, this will kind of show you, send you to the direction you need to go, okay? And also keeping track of your units and setting up the units with conversion factors and double checking your units, making sure the ones you don't want, if you cancel out properly, okay? So with that in mind, one more down the hatch here, okay? That ends chapter 13. I will like to